as we define the internal resistance, let me introduce this thing. So we have a battery or even a single cell. For example, we have a single cell, and along with that we have a resistor connected in series with it, and that completes the circuit. And then it is given in the question that the EMF of the battery is 9 volts. So as the current flows through it, since there is only a single component, we'll assume that the potential difference across the resistor would be 9 volts. And even if we try to measure the EMF of the battery, we connect a voltmeter, we would assume that the EMF would be 9 volt because it's given on the specification that the EMF of the battery is 9 volts. But the reality is, as the current flows, then the EMF or the voltage, I should say voltage, the potential difference that you get across the battery or across the single resistor would always be less than 9. Because the simplest reason is because the battery itself has a resistance, and some of the voltage out of 9 volts would be dropped across that resistance, which is the resistance of the very battery itself, which I've shown over here. This is the battery, this is the cell, and the internal resistance of the cell is shown over here and labeled as small r. Now this thing completes the battery, this thing. So in O-level physics, in IGCSE physics, we do not tell this thing. We just assume that whatever the EMF of the battery is, we're going to get the same voltage. But once again, like we say, terms and conditions applied with everything. You see at the bottom of all the promotions, terms and conditions applied. So it is 9 volts, but terms and conditions applied, some of it would be dropped against the resistance of the battery itself. And you can remove this resistance. You can just get rid of it. It could be any appliance. It could be a light bulb. You can simply remove the light bulb. But the thing is, the problem is you can never get rid of this resistance, which is the resistance of the battery itself. And that is dependent on the material of the battery, on the substance that converts the chemical energy into electrical energy. So we can never get rid of it. So let us define the internal resistance first. If they ask in the question paper, how do we define internal resistance? Well, let me write over here. Okay, so this is how we define the internal resistance of the source. Source could be a battery, it could be a single cell. Now let's take a look at the mathematics of it. So if this is the resistance R, small r, as you can see over here, and this is the resistance capital R, this is the cell itself, and more importantly, all of it is cell, including the resistance. But all you have to do is just to consider it as a circuit that contains two resistors connected in series. That's it. So it is a cell that contains two resistors connected in series. And E, this one capital E, is the EMF, the marked EMF of the source. If the label the EMF is 9 volts, so that would be the marked EMF of the source. But the actual potential difference across the battery would be slightly less than that. It could be 8.7, 8.8, 8.9, but it will not be 9 exactly as the current flows through the circuit. So what I can write is, if this is the overall EMF, then as the current flows, this one, as the current flows, some of the voltage would be dropped across this one, which is I times capital R, plus some of the voltage would be dropped across the other resistance, which is the resistance of the battery, aka internal resistance. So at this point, you can just consider it as another resistor which is connected in series. So the potential difference across that would be I times small r. No need to add any subscript with the current because current remains same in the series circuit. So it is just a series circuit that contains two resistors. One of them is capital R and the other one is small r. And then we can also write it this way. Capital E equals IR plus, this can be written as the voltage across the resistor. We generally represent it with capital V, the terminal voltage. And if I try to make V the subject, I'll be left with something like this, E minus IR. So the potential difference across the terminals of the battery, or the potential difference across the resistor that is connected, if you have a single resistor connected, would be represented by V, and that would not equal to the EMF of the battery. In no levels it does equal, but here we say that technically it is not equal, rather it is slightly less than the EMF of the source. How much? That much less. So it depends on the internal resistance, and from there we can find the voltage that is dropped across the resistance of the battery itself, and then we subtract it from the EMF. So I can write the same expression as something like this, IR plus E. Okay, just different ways of writing the same expression is 1, 2, 3, 4. All four of them are exactly the same. Mathematically, these are exactly the same, just a different notation. And once again, what do we call V? We call it potential difference across terminals of battery. Now I'm going to use this equation and I'm going to draw a graph of this equation. So let me write the equation once again. V equals to minus I, or let me write it this way, minus R and then I plus E. Okay, which is the same thing as above. That once again just a different way of writing it, but it's exactly the same thing. Mathematically it's just the same, just a rearrangement. Now the thing is, if I'm going to draw a graph, for example, let me draw a graph over here. So this is our y-axis, this is the x-axis, and on x-axis I'm going to label current and I'm going to label voltage, the terminal voltage on y-axis. So we are labeling these two quantities, this one being labeled on the x-axis and this one being labeled on the y-axis. What would the graph look like? It would be a straight line. How do we know? Because that replicates the equation of a straight line. Y equals mx plus c. Then you can see the relation. Like this one would be your quantity on the y-axis, this one would be your quantity on the x-axis, and CE would be your y-intercept, and negative R would be your gradient. So negative R would be your gradient. So gradient is negative, means the line would be upside down. It will start off with the maximum value and then it will keep decreasing and decreasing. And how do we know this would be an equation of a straight line? Because it's a linear function. We don't have any square, we don't have any square root, we don't have any cube, we don't have any exponential function, we don't have any trigonometric function, we don't have any natural log function. So it is a linear function. No square, no cube, and no exponential and all that stuff. So y-intercept is C, and the line will look something like this. This one. Okay, this is a graph of one of the source, and on the same one I'm going to draw a graph of another source with different internal resistance. So this is your battery 1, the source 1, and this is your source 2. And before I comment on the sources themselves, let me just write this thing over here. That gradient, as you can see through the equation of straight line, gradient equals to this thing, minus R. Likewise, y-intercept equals to E. So means this is your value of E, the EMF of the battery, the rated EMF, but we are not going to get the terminal voltage equal to the EMF that is rated on the battery. For the same reason, because there would be potential drop in the internal resistance of the battery also. Now the next question is, let's move on to the comparison. If I compare the graph of the first battery, battery 1, with the graph of the battery 2, the first question is, out of these two batteries, which battery has higher rated voltage? Which battery has higher EMF? Is it 1 or is it 2? Ramin. Question is, which one of these two batteries, battery 1, for which the graph is represented by the blue line?
Battery 1.
Okay, so the question is, which battery has higher EMF? So higher EMF means the rated EMF, the value of E. And over here, I have labeled them at the same point. The starting point is same, the y-intercept is same. So both of them would be having same EMF. Same for the battery 1, same for the battery 2. I mean, it might give you an impression that line 1 is slightly higher. It could be looking that way, but I was just trying to draw them from the same point. Okay, then the follow-up question is, the next question is, and this one is from you, Manur. Which one of these two batteries have higher internal resistance or more internal resistance? Is it battery 1 or battery 2? Same question, Ramin. Which one of these two batteries have higher internal resistance?
Battery 2 maybe.
And the reason being? The answer is right. And the reason being?
Because the value of current for battery 2 is lesser than for battery 1.
Yeah, you can totally answer that way as well, but the simplest explanation or the easier answer for you as well would be this thing: the internal resistance. Forget about the negative sign. Negative sign is just the direction of the line, it is upside down, the gradient is negative. Forget about the negative sign. But which one of these two lines have higher gradient? The answer is whatever line, what yeah, whichever line is steeper has a higher gradient, and gradient represents internal resistance. Hence, the battery 2 would have higher internal resistance. So battery 2 has higher internal resistance, as it has higher gradient. And then the follow-up question would be, and before I ask that question, let me once again label these things. Um, Gradient equals negative r, because the gradient would be negative, and hence eventually gradient would equal the internal resistance. Because whatever the answer of m is, for example, the answer of m is, it would be a negative number. For example, the answer of m is minus 0.5. Now what is that gradient equal to? That equals to minus r. So eventually resistance, internal resistance would be with the positive sign. Just keep it in your mind. So gradient equals to negative r, y-intercept equals to EMF, and then the question is, what does x-intercept equal to? So in order to find the x-intercept, for example, what does this point represent? This one over here, x-intercept. You can simply insert the value of v as 0, and then you can rearrange it for I, because it is on x-axis you have current, and if I rearrange it, for example, v equals to minus r times I plus E. Okay, this is the standard equation, but I'm going to insert the value of v to be 0, because only then you can get x-intercept. In order to find the x-intercept, the value of y has to be 0. So you write 0 over here, equals to minus r, and then we have to make I the subject, plus E. What do we get then? Well, you can shift Ri on the other side, equals to E, and then I equals to E divided by R. So this is what x-intercept represents, E divided by R. And you see, on x-axis we have current, which would be measured in amperes. So the answer, the unit of this expression, has to be amperes once again. And I hope both of you agree to this thing, that the unit of E over R would be amperes, because E is the EMF, which would be in volts, and resistance would be in ohm, and V over volt per ohm is your current. Matter of fact, the formula for the current is V over R. The EMF and resistance, but of a special kind. The voltage is not a random voltage, it is the EMF, the maximum rated voltage, the rated EMF of the battery. It's not a random resistance connected in series in a circuit. The resistance is internal resistance of the circuit. So this is what x-intercept equals to. Let's move on to the next page. And here we have a sample question. Two identical batteries. Okay, the circuit diagram is here. What is the internal resistance R of each battery? That needs to be found out, the internal resistance. And the current in the external resistor is 0.50 amperes given over here. So that means this current comes from here. That would also be 0.50 amperes. And the internal resistance needs to be found out. So what you can do is, you can think of it, you have two identical batteries, and the combined current of these two batteries is 0.50 amperes. So the first question would be, would we be able to guess the current of both the batteries? individual batteries for which the combined current is 0.5, but then what would be the individual current of both the batteries? First of all, it would be same because the batteries are identical. And how much would that be, Ramin? Can you guess the current drawn from a single battery? You see, the current of the two batteries once added up makes 0.50. Then what would be the individual current of the batteries? Same question, Manur.
0.25.
Okay, excellent. It would be 0.25 amperes. Matter of fact, it would simply be half of it. So 0.25 would be coming from there, 0.25 amperes would be coming from there. Only then we get a total of 0.50. There's no other way you can get a total of 0.50. I mean, you could get a current of 0.50 this way as well, but it would be inconsistent because the batteries are identical and they must be providing the same current. All right, so the next thing is, if we know the current through each battery, we can also say that the current passing through this resistor is 0.525 amperes, and through this resistor also 0.25 amperes. And what we need to do now is we simply need to find the resistance of that internal resistor. And how do we do that? Well, if we are able to find how much voltage is dropped across the internal resistance, we can then find the resistance of the internal resistance as well. Now forget about everything. Let's break it down into very basic steps. The EMF of this battery is 6. The EMF of the second battery is 6, which is connected in parallel with the first one, and that is then connected to a resistor with a resistance of 11 ohm. The EMF is 6 volts. If we do not compensate for the drop across the internal resistance, the EMF is 6 volts. EMF is 6 volts, and apparently if we are just an O-level student, we would assume that the EMF across the resistor would also be 6 volts. But the thing is, it's not going to be 6 volts. Can we find the EMF? Can we find the potential difference across this resistor? Yes, we can. Because in order to find the potential difference, you need to know this thing. You need to know the current passing through the resistor, and you need to know the resistance of the resistor. So we are provided with both the quantities. So 0.50 times 11, which would be half of 11 basically. So 5.5 volts. So you see, two batteries have rated EMF of 6 volts, but the resistor that is connected across those batteries in parallel is not getting 6 volts, it's getting 5.5 volts. So it's very hard to explain this thing in for a question of O levels. I mean, what do we say? Where is the extra voltage dropped? 0.50. Where's that dropped voltage? But now we know the drop voltage is dropped across the internal resistance of the battery. So 0.5 would be dropped over here, 0.5 would be dropped over here. So in reality, you have this thing. So it was not 6 volts in the first place. The voltage that you were getting from the battery was only 5.5 volts. And thereby, the voltage across the resistor would be 5.5 volts. So how do we answer that? We say we were never getting 6 volts in the first place. The potential difference across the battery was 5.5 volts because 0.5 volts is dissipated or dropped across the internal resistance. Now, you can use either of it, the upper one or the lower one. Let's consider this thing. If we know the potential difference across the resistor, and if we know the current passing through the resistor, can we find the resistance itself? Ramin?
Yes, sir.
How do we do?
Using the resistance formula, which is R is equals to V over I.
Thank you. Very good. R equals to V over I, and voltage in that case across the resistor. Okay, just be very careful. Do not write 6 here. Do not write 5.5 because the resistance that is dropped across the internal resistance is 0.5. And the rule of thumb is it's always going to be a very small number. Like probably 5% of the what do you call that, of the EMF itself. So for 0.5 from here and 0.25 from here. So 0.25 is basically 1 over 4. That 4 would be shifted upward and you will be left with 0.5 times 4 would be 2. So if you hit it on if you would hit it on the calculator, I think you're going to get the answer 2.